Welcome to this course on Elements of Mechanical Engineering. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. So, we are in the second module where we are studying boilers and turbines. So, this is the module which is related to the working of different types of boilers, where we study different types of turbines. In the previous lecture, we have seen the working of any kind of simple turbine. We have seen the basic definition of turbine, we have seen classification of turbine and different terminology and the formulas related to efficiency of the turbines. Now, in this lecture, we are going to study the working of Pelton wheel turbine and different calculations or formulas related to the design of the turbine. Let us see what is a Pelton turbine. So, this is a turbine which was developed by a scientist named George Pelton. So, Pelton is the name of the scientist. So, this is the only type used in high head power plants. This type of turbine was developed by L.A. Pelton in 1889. Back in the year 1889, it was developed by Pelton. So, this is a simple Pelton turbine. Like, it is a simple form of any turbine which will have an open atmospheric condition. The pressure inside the turbine is very open to atmosphere. There are no restrictions, there are no pressure differences when compared to atmospheric pressure. Now, let us see the main components of this turbine. So, the main components are like runner. So, runner is the key thing which will rotate when water falls on it. We have already seen how the turbine will work. So, this is the runner part, where when water touches the turbine vanes or buckets, so these small things, these are called vanes or buckets. When water falls on these, they will create or they will exert some force on this turbine vane. Now, when the force is exerted on this vane, it will try to rotate. Now, when the turbine will rotate, it will create a mechanical energy that is in the form of rotational form. Okay, so the mechanical energy produced here is in the rotational form. Now, this is the first component of the Pelton wheel turbine. So, this is runner with buckets fixed on the periphery of the runner. Okay, now this central part, this is the runner. On this runner, we have these small vanes attached to it. So, this entire thing, the runner buckets arrangement is fixed on a shaft, cylindrical shaft at the center. Now, this cylindrical shaft will also rotate along with the runner. Now, this turbine shaft is connected to a generator shaft where it will make the generator rotate and it will produce the electricity. Now, the second part is the nozzle assembly with control, sphere and deflector. Now, see here, this thing is called nozzle and sphere arrangement. Now, what is the function of this nozzle and sphere arrangement? So, this nozzle and sphere arrangement is used to control the flow of water that is coming out of the nozzle. So, we have seen in the previous lecture, the function of a nozzle is to increase the pressure and velocity by a decreasing cross-sectional area. So, this is a pipe for which the cross-sectional area is decreasing. It is decreasing varying cross-sectional area. When the water tries to passes through this nozzle hole, it will come out at a faster speed. The velocity of the water will increase. So, in order to give more pressure or more velocity for the water, we use this nozzle. Now, inside this nozzle, we use a device called sphere. Sphere is nothing but it is a metallic rod which is in this shape, conical shape. Now, the sphere is used to control the flow of water that is coming out of the nozzle. When it is pushed towards right side, less water will come. When it is pushed back to the left side, more water will come out of the nozzle. Now, the deflector, we have seen in the second component, it also has a deflector. So, what is the function of the deflector? So, deflector is nothing but it is a small metal rod kind of thing where it will deflect the flow of water. Okay. So it will try to move the water towards the bucket. So bucket is nothing but the small connections that are attached to the turbine wheel. They are called buckets. So the function of this deflector is to make the water to flow towards the bucket. Okay, so that it will create more pressure on the bucket surface, which will make the bucket move. Along with the movement of the bucket, the turbine will rotate. Runner will rotate. So here we can see there are number of buckets placed on the turbine wheel. So each and every turbine wheel will move continuously when water is falling on them, which will create a rotary motion. Okay. Next, third one is brake nozzle. So in this diagram, we can see there is a small nozzle arranged in this place. So what is the function of this nozzle? So the function of this nozzle is to stop the turbine when it is rotating at very high speed, or to control the speed when it is going above the limit. Okay. So the function of this brake nozzle is simple. There are two functions. First one is it can stop the turbine to rest position, and it can slow down the turbine. So we know that this turbine is connected to a generator. Generator required a rated RPM. So in order to get the rated RPM, this turbine has to rotate at a particular speed. Now what happens is, here the turbine is rotating with the power that is coming out of the nozzle. So water coming out of the nozzle, it will have some power. This power is used to rotate the turbine. When the turbine is rotating more than the rated RPM of the generator, then we have to control it. Okay. So in order to do that, we have to use a separate nozzle through which water is coming, but this water will touch the buckets on the back side. See here, this water is coming in this direction and it will hit on this side of the bucket, on the left side of the bucket. Whereas this braking jet, here the braking jet water is coming in this direction and it is hitting at the back side of the bucket. Okay, the other side of the bucket, it is hitting so that it will reduce the speed, or it can completely halt the turbine runner. Okay, so braking nozzle or braking jet is the one which is used to stop the turbine from rotating. Okay, or it can slow down the motion. And then the fourth part is casing. See, in this picture we have a hemispherical casing which is attached on the turbine wheel. So the function of this hemispherical wheel is to control the splashing of water, because water is coming at a high speed from this nozzle. It will touch the bucket vanes, and from bucket vanes, when the turbine is rotating at higher speed, the water will be splashing in all directions because it is moving in rotation motion. So water will be splashed in all directions. So every water has to be controlled and it has to be collected at the tail race. See here, the tail race is there. Tail race is the place where the water that is coming out of the turbine will be collected. So we use this casing. So the casing will collect the water. It will not make the water to flow away in all directions. It will collect the water and the water will eventually comes down. Okay. So whatever the water that is there, it will comes down to the tail race. So these casings are generally made up of concrete, like big concrete hemispherical structure, or sometimes they are made up of metal, like cast iron. So the simple function of this casing is to control the splashing of water when the water is running on the turbine. So these are the main components of any Pelton wheel turbine. So it is very simple. So the basic difference is, like the basic concept of this turbine is, water coming out of the nozzle will touch the bucket and the bucket will move. Eventually it will rotate the turbine. Okay. Now we have a casing which will collect the water and the water will be collected in the tail race. And we have a braking nozzle which will reduce the speed of the turbine by applying the water jet force on the back side of the bucket. Okay. Now, so let us see the construction of the Pelton wheel turbine. So the rotor or runner consists of a circular disc fixed on suitable shaft made up of cast or forged steel. Okay, we have a rotor which will be rotating. So the rotor consists of a circular disc. Okay, we can see in this picture, this is already discussed here. So the central rotating part of this turbine is fixed on a shaft. This is a horizontal shaft on which we will fix a circular disc. Okay, so that is what written here. So the rotor or runner consists of circular disc fixed on suitable shaft made up of cast or forged steel. And then second one is buckets are fixed on the periphery of the disc. So we can see these small things are called buckets, and these are fixed on the periphery, that is outer side of on the circumference of the disc. Now the spacing of the buckets is decided by the runner diameter and jet diameter, and is generally more than 15 in number. So the number of buckets on the runner will be more than 15, and the actual number of buckets will be calculated by using a formula. We'll discuss it later. So it depends on the diameter of the nozzle and also diameter of the disc. So it depends on this diameter of the disc, and also the diameter of the nozzle through which the water is coming. Okay, depending on that, we will place a bigger bucket or a smaller bucket. We have to decide depending on the diameter of the nozzle also. And then the spacing is done. These buckets in small sizes may be cast integral with the runner. So if the buckets are very small in size, that means we are using a smaller type of turbine. Then what happens is this entire turbine, entire runner along with the buckets will be casted. So these buckets are not separately made and they are fixed on the casting, fixed on the runner. They will be integrated in the casting itself if the runner is very small in size. If the runner is very big, like if we want to use the runner for a very big hydraulic power plant, we have to design the buckets separately, and these buckets have to be attached to the periphery of the runner. And then in large sizes, it is bolted to the runner disc. So that is what we said now. So if the turbine wheel is very big, the buckets has to be bolted. They have to be fixed on the periphery of the runner. Okay. So in this diagram, we can see this is the cross-sectional view of the bucket. So see, the bucket is not simply a curved shape structure, but it is very complex. Like it will have two curves. Okay, like this. This is one curve and this is one curve. Why we have to place this kind of structure in Pelton wheel turbine? So if the runner is simply like this, I mean if the bucket is simply a one curve, what happens is when the water touches at this center point, on one side we will have the disc, this is runner. On the other side the water has to come out. Okay, the water has to come out in this direction only. What happens is when the water is touching at the center of the bucket, it will splash or it will divide into two directions, one in this direction, another in bottom direction. Now what happens is this will create some storage of the water in the bucket. So whenever we take at any instance, we will have some water that is present in the bucket. So in order to control that, we have designed the bucket in this shape. So this is the shape. This is the shape of the bucket, which will have two curvatures. So the water will try to touch at this point, that is here. So when the water is touching at this point, it will be divided into two parts. One in this upper direction and another one is in the bottom direction. So because of this two curvature design, water will be easily removed. Water will be easily removed from the bucket so that no water will be stored in the bucket when the turbine is rotating. Because every time we will be running the turbine at a very high speed, like 400 to 500 RPM. That is why we have to continuously remove the water. So the design should be done in such a way that water will be coming out of the bucket very fastly. Okay. Now we have some different formulas here. This is jet diameter. This is the jet of water which is touching the bucket. So we have diameter D, small d, and we have a certain angle here, 10 degrees to 15 degrees angle, that is done for each curvature. Like this angle with respect to horizontal, it will be 10 to 15 degrees. Okay, this is the angle. And then we'll go to the next slide. So let us see, some equations are there related to Pelton wheel turbine, which are going to be calculated while designing the turbine, while we design the turbine bucket or turbine design. So we have to use these formulas. So equations are available to calculate the number of buckets on a wheel. The number of buckets is denoted with capital Z. This one, we have to use this formula in order to calculate how many number of buckets should be available or should be attached on the runner. Okay, so let us see this formula. So capital Z, which is the number of buckets, is equal to capital D divided by 2 times the diameter of the jet. So here capital D is the diameter of the runner and small d is the diameter of the jet of water. So from this formula, we have to add 15 because we have said already that each turbine runner should have at least 15 buckets in order to have a perfect motion. So along with this 15, we have to add this value like capital D by 2 into small d, which stands for diameter of the jet. So this will give you how many number of buckets should be added along with 15 number, so that we'll get the number of buckets on the runner. Okay, and now we have some design formulas here. Capital D by small d. So this ratio will always lies between 14 to 16. And capital B by small d, it will lies between 2.8 to 4. And capital L is the length of the jet and small d is the diameter of the jet. So this ratio will stay between 2.5 to 2.8. And capital T by D. So this ratio will be always 0.95. And also we have notch width. So notch width also has to be calculated while designing the turbine. So its value will be 1.1 D plus 5 millimeters. So this depends on the diameter of the jet. So we have to design the notch based on the diameter of the jet that is coming out of the nozzle. So we have different types of arrangements here. So this is first one. We have a simple nozzle spear arrangement in which we can see the flow of water. Okay, so these two are normal, where we will push in the spear or push back the spear so that the water flow can be controlled. And in the second diagram, the bottom diagram, we have deflectors which are placed at normal orientation. So the function of this deflector is to control the flow of water. And then the last picture, we can see when the deflector is moved towards down, okay, we can actually change the flow of direction. Okay, in this picture, we can see this is horizontal. The water is flowing horizontal. So if this deflector along with this metal plate, if it is moved downwards, we can actually change the direction of flow. We can deflect the flow of water. Okay, see here, the water is flowing in this direction. So the function of this deflector is to change the water flow so that we can change the movement of the turbines according to the speed. So this is how we can calculate the number of buckets on a jet, the number of buckets on a runner. And then we'll see the construction of the velocity triangle for Pelton wheel turbine. So the bucket splits the jet into equal parts and changes the direction of the jet by about 165 degrees. Velocity diagram for Pelton wheel turbine is drawn here. In the previous slide, we have seen the turbine bucket is designed like this. We have two jets. We have a jet that is touching at the center and it will be deflected into two parts. One in this direction, one is in the upper direction, another one in the bottom direction. Now, we have to analyze the velocity of the water that is touching the bucket, and we have to calculate different velocities based on which we will calculate the efficiency, power generated, etc. So now we will take this half part, only half bottom part is taken into this calculation, and we will analyze the different velocities of the water that is touching the bucket. So this is the bucket vane. This is only half hemispherical shape which is taken into consideration. and we will analyze the velocities, different velocities, and we will draw the velocity diagram also. Now see here, we can see this in this direction water is coming and it is touching this bucket at this point, and it is traveling all the surface, along all the surface, and it is coming out in this direction. So this is the basic thing happening in this bucket. Water is entering at this point, let this point be 1, and water is leaving at point 2. Now we have different velocities. See here, we have V1. V1 is nothing but velocity at inlet. Simple velocity of water at inlet. And then we have V2. V2 is the velocity of the water at outlet. Okay. And then we have VW1. VW1 is not written here, but VW1 will be calculated later, which is whirl velocity. Whirl velocity at inlet. So all VW1s or V1s, the notification, the denotation of 1 will be at point 1. That means at the inlet. At outlet, we will denote everything with 2. And VW2 is the whirl velocity at outlet. So this is how we will calculate different formulas that are related to the velocities. So see here, U is the velocity of the turbine. U is the velocity of the turbine, and along with U, we will have U1 and U2. That is velocity at inlet and velocity at outlet. So because the bucket shape is curved, they are not moving at the same speed, and also they will be at different positions when we compare it to a circular motion. Okay, so this point 1 will be near to the shaft and point 2 will be away from the shaft. Because of this, these 2 points will have different velocities. That means the velocity of the bucket will be different at point 1 and 2. So depending on this, we have to take the velocities of the bucket separately, whereas U1 plus U2 will ultimately give you the velocity of the bucket. Okay. Now, so these are some of the formulas, like the denotations where we will use different types of where we will calculate the velocities. So in this case, the jet direction is parallel to the blade velocity or the tangential velocity of the runner. See here, we can see the water is coming in this direction, horizontal direction, and it is touching at point 1. So the direction or the velocity of this direction of flow of water is parallel to the movement. Okay, so that is why we have seen VU1 is equal to V1. VU1 is nothing but the whirl velocity. Okay, so VU1 is equal to V1. And then if we calculate relative velocity, VR1. So VR1 stands for relative velocity at point 1, which is equal to V1 minus U. V1 is the velocity of the water coming out of the jet, and U is the velocity of the bucket. Okay, now how we can define the relative velocity? Suppose, in order to explain the relative velocity, I will take an example like VR, relative velocity. Suppose there are 2 cars which are moving at different speeds, like car A is moving at 100 kilometers and car B is moving at 80 kilometers. Now, what is the relative velocity between these 2 cars, A and B? So we can see that car A is moving at 100 km speed and car B is moving at 80 km speed. Now, if we want to calculate the relative velocity between these two, VR will be 100 minus 80, which will give you 20 km per hour. So this 20 km per hour is the value of the relative velocity. So when a person is standing at the on the road at a stationary point, if he watching the cars with respect to the person, car A will be moving 100 kilometers per hour and car B will be moving 80 kilometers per hour. Now, if a person is sitting in car B and if he is looking at car A, the car A will be moving at 20 kilometers per hour because the person who is sitting in car B itself is moving at 80 kilometers per hour. Okay. Now, this is a simple explanation for relative velocity. Okay, the relative velocity is very simple. Like when two bodies are moving at different speeds, the relative velocity will be the difference of the speeds of those two cars, of the two bodies. Okay, when we compare the speed with a stationary person standing on the road, the speeds will be different. Like car A will be moving at 100 kilometers and car B will be moving at 80 kilometers per hour. So similarly, in this explanation, that means in the construction of the velocity diagram of our turbine bucket, we have to use this relative velocity between the water that is coming out of the jet, that is the velocity of the water coming out of the jet is taken as v1, and u, the velocity of the bucket. The bucket is moving and the water is coming out of the nozzle. So the relative velocity has to be calculated. Okay. Now let us try to imagine that we are sitting at point 1. Suppose I'm not I'm not standing on the road. I'm sitting in the car B. Like that, I am standing at this position point 1. Now when I calculate the relative velocity, I have to take the values v1 minus u, which will give you the relative velocity between water jet and the moving bucket. Okay. Now this is the relative velocity and this is the velocity of the jet. Now we'll see some more formulas. In ideal cases, we have VR1 is equal to VR2. So VR is nothing but the relative velocity between the water jet and the bucket. So at VR1, we have relative velocity at inlet. That means water jet and bucket are moving at the different speeds. And also we have VR2, where the water jet and water coming out of the bucket will have some relative velocity. Relative velocity at outlet. Okay. And see here, in most of the cases, VR1 is almost equal to VR2. So the difference is neglected and it is taken equal. And then due to friction, we will have some correction factor. So when the water, this is the bucket, when the water is entering in this point and it is traveling along the surface of the bucket and it is leaving at this point. So when the water is traveling on the surface of the bucket, it will have some friction because it is a metal body and it will have some friction. So due to this, we have to add a friction factor between VR2 and VR1. So VR2 is nothing but equal to K times the VR1. So relative velocity at point 2 is equal to K times relative velocity at point 1. And also we have velocity of the buckets, that is U1 and U2. These two are generally taken as equal because the movement of the bucket is almost, because the buckets are very small, the velocity at point 1 and point 2 are almost equal. Okay, in most of the cases it is equal. When we take the real-time conditions, they will be different. We are considering an ideal condition, so that is why we are taking this as equal. U2 is equal to U1. And then if we calculate the force that is being exerted on the bucket, we know ultimately our goal is to exert some force on the turbine wheel so that the turbine bucket will move the turbine. So we will calculate the force. The force value is equal to mass is nothing but the mass of water coming out of the jet, mass m into VU1 plus or minus VU2. So VU1 and VU2 are the whirl velocities. Okay, whirl velocity. Whirl velocity is defined as the velocity with which a turbine will rotate. Okay, whirl velocity. Whirl velocity. Generally it is denoted with VW, but here in this condition it is denoted with VU. Okay, so whirl velocity is the key thing which will make the bucket move. Okay, it depends. It is a key source which is creating some force. That is why it is taken in this formula. And here force is equal to mass times VU1 plus or minus VU2. Whirl velocity at inlet plus or minus whirl velocity at outlet. And also we can calculate the torque. So simply we will multiply the radius of the bucket, radius of the runner and we will get torque. Because it is a rotational body, we can calculate torque also, and from this we can calculate power. So the power is nothing but the force multiplied by the distance, or simply the velocity u. Okay, where m is given by, here m is the mass of the water, so m is calculated by rho AV. Rho AV stands for, rho is the density of water, that is 1000. Like capital A is the cross sectional area of the jet, and V is the velocity of the water that is coming out of the jet. Okay, so m is equal to rho AV, and hydraulic efficiency of this entire thing can be calculated. We have seen in the previous lecture the hydraulic efficiency. We have some formula. So from this we can calculate the hydraulic efficiency as mass times world velocity at point 1, world velocity at point 1 plus or minus world velocity at point 2 multiplied by the velocity of the bucket divided by mass times V1 square by 2. So this is half mv square, that is kinetic energy that is available at the jet. Okay, so upon modification or simplification, we will get this formula: 2 times u v u1 plus or minus v u2 into the velocity of the bucket divided by velocity of the jet square. Okay, once the effective head of the turbine entry is known, we can calculate this value also. V1 is equal to the coefficient of velocity multiplied by 2gh. G stands for gravity and h is the head of the water present in the dam or the head race. For various values of u, power development and efficiencies will be different. Okay, now we have some more formulas. It is desirable to arrive at a optimum value of u for a given value of v1. Here u is nothing but the velocity of the bucket, and v1 is the velocity of the water that is coming out of the jet. Now hydraulic efficiency equation can be modified by using the following relations. Okay, let us see those. We have seen this is the hydraulic efficiency formula. Okay, this formula can be modified accordingly in order to make it small. Okay, we will use some more equations like VU1 is taken as V1 and VU2 is taken as VR2 cos beta. So this entire thing can be done with the help of a triangle diagram that is taken from the velocity triangle, and we have to calculate these values, and finally we will arrive at this value. So the hydraulic efficiency is equal to 2u divided by v1 square. If we see the formula in the previous slide, 2u divided by v1 square is same. These two are constant, they are not changed, and in the place of vu1 plus or minus vu2 multiplied by velocity of the bucket. Now this is changed. This entire thing is changed, like 1 plus k cos beta 2 multiplied by v1 minus u. So upon simplification, we will get this formula like 2 times 1 plus cos beta 2 multiplied by u by v1 multiplied by minus u square by v1 square. Now see here, this u by v1, it is the ratio of the speed of the bucket divided by speed of the jet. Now this ratio is denoted with phi. Okay, now this ratio is called phi, it is denoted with phi, where we will simplify the hydraulic efficiency formula. So the hydraulic efficiency is nothing but 2 times 1 plus k. K stands for the constant of friction, cos beta 2, and cos beta 2 is the angle of the bucket. Okay, angle of the bucket which is inclined, and then we have u, velocity of the bucket, v1 is the velocity of the jet coming out of the nozzle, and here also u is nothing but the velocity of the bucket and v1 is the velocity of the jet. Okay, so this is the simplified formula for hydraulic efficiency of a Pelton wheel turbine. So therefore, we have, after modification, we will get this formula like pi minus pi square. So we have seen that we are representing the value of u divided by v1 with this phi. So we can write this formula as 2 times 1 plus k cos beta 2 phi minus pi square. To arrive at this optimum equation, the expression is differentiated with respect to omega and equated to 0. Okay, so we are going into deep simplifications where we will differentiate this equation with phi. So 2 times 1 plus k cos beta multiplied by 1 minus 2 phi. So this is a very simplified formula where we will get phi is equal to u by v1. This is the basic formula. This is equal to half, which means u is equal to 0.5 times v1. So from this equation, we can understand, and we have to remember this formula. When we calculate the velocity of the bucket, it is 1/2 of the velocity of the jet, okay, which is indicating that the force that is coming out of the nozzle is utilized only 50%. Only 50% of the force or the velocity coming out of the nozzle is converted into the movement of the bucket. Okay, u is the velocity of the bucket and v1 is the velocity of the water that is coming out of the bucket. So we can simply understand from this formula that the velocity, only 50% of the velocity of the jet is converted into the velocity of the bucket. Okay, and then we have some more modifications for this formula. We have substituted this u value in this, and we have got this 0.5 minus 0.5 square, and finally we got this formula. This is very simplified form of the hydraulic efficiency. So when k is taken as 1 and beta is equal to 180 degrees, that means the bucket angle is almost 180 degrees. That means it is flat. Then we will have 100% efficiency. So here we can see here NH or efficiency, hydraulic efficiency is equal to 1, or it is 100% equal. So when this is 100%, when we will get 100% efficiency, when the bucket is inclined at 180 degrees centigrade. 180 degrees. That means the bucket is flat to the direction of flow of water. So this is when we will get 180 degrees. So the water that is coming out of the jet will be completely touching the bucket, and the bucket will move at 100% of the efficiency. But in actual conditions, the efficiency will be designed between 85 to 90%. The hydraulic efficiency value always lies between 80%, 85 to 90%. It will be never 100% because we cannot design such a bucket which will give you 100% efficiency, because we have some practical problems like the water will stay inside the bucket, or the water will not be removed easily from the bucket, and it will not, there are some production issues where the bucket cannot be manufactured. So next, let us see the design aspects of a Pelton wheel. We have velocity of the jet, velocity of the wheel, angle of deflection of the jet, and mean diameter of the wheel. So the velocity of the jet is nothing but V1 is equal to CV root over 2GH, 2 times gravity multiplied by head raise. Okay. So the coefficient of velocity, it always lies between 0.98 and 99. It is a standard value, it is taken as constant. And velocity of the wheel can be calculated by using this formula. U is equal to K times root 2GH, where the value of K varies from 0.43 to 48. It is a constant value. And the angle of deflection of the jet. The angle of deflection is almost taken as 165 degrees. When the value is not given in the question or any numerical example, we have to take it defaultly like 165 degrees. Okay. And then mean diameter of the wheel. So the mean diameter can be calculated by using this formula. Capital D is equal to 60 times the velocity of the bucket divided by pi multiplied by number of jets. Here capital N stands for number of jets, where capital Z stands for number of buckets. Okay. So if you want to calculate the diameter of the wheel, we have to take into consideration the velocity of the turbine and also the number of jets that are hitting the water on the turbine. And we have jet ratio. The jet ratio is nothing but small m is equal to capital D divided by small d. Capital D stands for the diameter of the turbine runner and small d is the diameter of the jet. And it is mostly taken as 12 for most of the cases, and also depends on the, due to the design problem, we have to take this around 12. And then we have another formula for number of buckets, which is already discussed. Z is equal to capital D by 2 times the small d plus 15. So this value will almost be here. This can be modified, and this ratio can be almost taken as, just now we have seen here, this is taken as 12, capital D by small d. Here 15 plus, so this is taken as 15, simply it is written again, because we should have 15 as the minimum number of buckets. And capital D by 2d can be written like capital D by 2d, capital D by small d is small m, so we can write m by 2. So this is simply written as m plus 0.5 into m. Okay, 15 plus 0.5 into m. And also we can calculate number of jets. It is obtained by dividing the total rate of flow through the turbine by the rate of flow of water through a single jet. Okay, this is how we can calculate the number of jets. So number of jets is nothing but it is denoted with capital N, and it is calculated by dividing the total rate of flow through the turbine. So total rate of flow that is coming out of the turbine by the rate of flow water through a single jet. Okay, so this is the total rate of flow and this is through a single jet. So by using this formula, we can calculate how many number of jets are required for running the turbine. Okay, so these are some of the design formulas. So far we have seen, we'll recap everything. Like we have seen the main components of the turbine. There are 4 components: runner, nozzle, braking jet, and casing. These are the main 4 components. After that, we have seen the construction of the bucket, which is double spherical shape, like double curved shape, where the water will touch at the center and it will be deflected into 2 directions. So the angle will be almost 10 to 15 degrees here. And also we have seen the formula for number of buckets. It should be more than 15. For that we have to add this value, capital D by 2D, so that we will get the final value. And then we have Pelton wheel turbine velocity diagram, where we will calculate the different velocities like V1, V2, VU1. So this is VU1 and this is VU2. So where V1, V2 are the velocity of the water at inlet and outlet, and VU2 and VU1, these are the world velocity of water. And then we have U, which is the velocity of water, velocity of the bucket. And then we have Pelton wheel calculation, like we have calculated force that is exerted on the bucket, and we can calculate the torque with which we can calculate power. And also we have calculated hydraulic efficiency, where we got simplified equation for hydraulic efficiency, that is this one, 1 plus K cos beta 2 by 2. Here beta, if it is ideal condition, beta is taken as 180 degrees and K value is taken as 1. So this is the constant of the runner. When in ideal condition, we will get 100% efficiency. But in practical condition, the efficiency of the hydraulic turbine stays between 85% to 90%. And after that, we have seen different design aspects for Pelton wheel, where we can use different formulas for calculating velocity of jet, velocity of the wheel, angle of deflection of the jet, with which angle we have to deflect the water that is coming out of the jet, and mean diameter of the wheel, capital D. And also we have calculated jet ratio, number of buckets, and number of jets. So that's all for this class. We'll meet in the next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.